symmetric differentiation. All right? So I take a partial g partial x, I got a 3, all right? I got a partial f partial y is equal to minus 4. So these two are not equal. So this guy is definitely not conservative, aka not irrotational, aka there's no way you can find a scalar function such that it is the potential function, aka you cannot make it a line integral to 0 for all the closed smooth curve. Okay? In other words, there are definitely closed curves that you take the line integral or the circulation along this closed curve. It's not going to vanish. Okay? So this is all coming from a simple checking here. Okay? And now I'm going to give you the smooth curve. The smooth curve is given by a region which is the boundary of a sine curve. So this is y is equal to sine x, and also y is equal to 0. Okay? So this curve is given by y is equal to sine x, and the other part of the boundary is given by y equals 0, which is the x-axis, between x is 0 and x is equal to pi. So essentially, this is the region, and the smooth curve is the boundary of this region. Are we clear what we're talking about? Okay, so I have a sine curve between 0 and pi. Okay, and this region is bounded above by sine of x, below by x-axis, and this is my region right here. Okay, and the smooth curve is given by the boundary of this region oriented in the counterclockwise direction. Okay, so this is my thing. Any questions what this object is? So this is basically two pieces of the same smooth curve, right? So two piecewise curve. One curve is given by this x-axis. The other piece is given by the sine curve, right? That with me? Okay. Now I want to compute these two objects. I want to compute the line integral on the boundary. I also want to compute the double integral in the interior. Okay? Double integral in the interior of the curl. So this guy, the curl of the function, is equal to partial g partial x minus partial f partial y, which is equal to, what is it? Partial g partial x minus partial f partial y is going to be 3 minus 4. I got a 7 right here. Okay? So if I look at this problem, which I want to compute the line integral on the boundary and double integral in the interior, which one do you think is easier? Which one do you think is easier? We're going to do both. So no matter which one is easier, we're going to finish both of them. Which one do you think is easier? The double integral is definitely easier, right? So the double integral of the interior is the double integral of the constant function 7 in this region. This region is extremely easy in double integral case. So in double integral case, let's refresh our memory. X simple, y simple, polar, and r simple, and also change of variable. Which one is this guy? It's just the y simple region, right? X goes from 0 to pi, y goes from 0 to sine of x, right? So double integral in the interior is just from 0 to pi, from 0 to sine x, because this region is a y simple region. And the constant function 7, because it's a y simple, I want to do dy first and then dx. Okay? So this is double integral in the interior. Okay, so let's clear off this double integral step by step. This is a pretty easy evaluation here. So from 0 to pi, 7 dy, and then this is going to give me 7 sine x dx. All right? And I pull 7 out. The integral from 0 pi sine of x is going to give me 2, actually. So it's going to give me a 14. Again, this part of the problem is not what our main focus on. But of course, you have to be able to do that. Okay? If you have trouble with doing the single variable calculus, you have to come to me afterwards. But in class, we're going to focus our whole energy into how to reduce the original problem into a single variable calculus. Okay, that's our main focus. Again, I give you a lot of small tricks you can play around with, not play around, you can use in test and final. This is a double integral of a positive function. It's not going to give you any negative number in the end. Okay, so if you end up with a negative number, you have to be super careful. Yep.
A line is supposed to be negative, right?
The line integral is not going to be negative, but we're going to do that.
I'm not saying for this one, I'm saying could it be negative?
Yeah, the line integral and double integral, they can all be negative, but it depends on the function and the region, right? This region, my integrating function is a positive number, so it has to be positive integral in the end. There's no way you can integrate a positive number and get a negative number in the end, right? So this is the easy part. Then I'm going to do a line integral on the boundary. So the line integral on the boundary compared to the double integral is more complicated, simply because you have two pieces of the boundary, right? A linear piece and a sine curve. You have two pieces of linear curve. And also we have to find the parametric form for each one of them separately. Right? These two have to have two different parametric forms. There's no way you can have them to be written down in the same form, because one is linear, the other one is not. Okay? So I'm going to spend major time in talking about how to find line to the boundary, or I'm going to repeat this multiple times so you know what they're the same. The circulation of the vector field on the boundary. Okay? So let's look at the easier piece, which is the linear piece. So the linear piece is going from 0 to pi on x-axis. Okay? So remember, when we want to derive our parametric form of any piece of the curve, we have to have the two equations for x and for y. All right? So basically, I want to have this piece C1 defined by r of t is equal to xt and yt. I should have two parts of the equations, right? So I have two parametric equations define x component and y component. But remember, that's not the whole story. For any parametric equation, we also have to have t goes from where to where. All right? So every time, as long as you're dealing with a line integral where you need to find a parametric equation, remember, not only you have to have two equations, but also you have to have two numbers for the initial time and the terminal time. This part is the easy one. RT as the linear piece is lining on x-axis, so the y component has to be 0. All right? Y component has to be 0. What do you want the x component to be? You can simply name it t. All right? You needed to introduce a new parameter. So you have to assign a role for this parameter. So the easiest way to assign the parameter t here is just it equals x. All right? X from 0 to pi, then t has to go from 0. All right? And then I take the integral in this piece, C1 piece, which f dot dr is what we need to compute. Okay? Remember, when you compute the line integral, you have to plug in your parametric equations in two different places. One is to the vector field. The other one is take the derivative to get the tangent. All right? So one you have to plug in is f. The other one you have to take the tangent vector. So this part I have minus 4y 3x. So if you're not very smooth about this, let's do it separately. And dr is taking the derivative with respect to t here. So it's just 1, 0 dt. Okay? And then we plug in whatever is needed for y and x. Here I have minus 4, y is equal to 0. So this part is simply just 0. X is equal to t. So this is just 3t. Dot 1, 0 dt. So this dot product between two orthogonal vectors, actually, right? You're going to get 0, 0. So this line integral contribution is going to be 0. Okay? I want every one of you to know follow what we're doing here. We're doing the line integral. We need a parametric equation. We need an initial time and terminal time. We need a plug-in for vector field. We also need to take the tangent vector by differentiation. Okay? Okay, so one side note here. The parametric equation for the curves are usually not unique. You can't design your parametric form differently by changing the equations, but also you have to change the initial time and terminal time. Here, my parametric equation is given by t0, where t goes to from 0 to pi. I'm saying I can also modify this part to make my parameter to go from 0 to 1. But I have to modify my parametric equation a bit. Okay? Instead of having t here, I have to have a pi t. So I can also have my parametric equation to be defined by pi times t is 0, where t goes from 0 to 1. Okay? These two are both defining exactly the same curve, but they have a slightly different form. If I change one, I have to also modify the other one. In the homework, in the online homework, they always want you to find the parametric to be going from 0 to 1, so that you have to change your equation a bit. But if you have a linear equation, this linear equation will be completely determined if you fix two boundary points. In our check, this is still the same curve. I only need to check 2 points, and that's sufficient. Now with me? I only need to check the initial time. For t equals 0, I'm getting a 0. When t is equal to 1, I'm getting a pi, which are exactly these 2 points. And it is linear, so I'm done. Okay? For linear equations, you can easily change your equations and the range of the parameter to get the same curve. Okay? You only need to check the 2 boundary points to make sure this is the correct parametric form. Questions? Yep.
So the reason why we're going the r vector is t0 is because we're only doing the first piece, right?
Mm-hmm. We're only doing the first piece, exactly.
So
okay.
We haven't worked with the sine.
We haven't worked the sine curve yet.
Yeah.
Okay, so the difficult part is actually give a parametric description of the sine curve. Okay. So in the sine curve part, let's see what we can do. So this is the linear piece. So let's look at the sine piece, where C2 is going from, remember, we have to be super careful. We can easily have a parametric equation, but also we have to make sure this point is where it begins and this point is where it ends. Okay? I have to make sure this point is the initial point, this point is the terminal point. Initial point, terminal point means when I find a parametric equation and I plug in the initial time and terminal time, I'm supposed to make them these 2 points correspondingly. Okay? So you already have this equation y equals sine of x. Okay? You already have it y equals sine of x as the equation of the sine curve. I need to introduce a new parameter. So the straightforward one you can introduce it is what? X equals t, y equals sine t. All right? X equals t, y equals sine t. And you have to be super careful about where it begins and where it ends. So if I want the t to begin from pi, I want this point to begin from 0 pi, right? So this, pi 0. Pi 0 is this point ending at 0, 0. Where is your initial time? How do you want to set up your initial time? So this is where x equals pi, the initial time, right? Mm-hmm. So if I make t equals x, so the naive choice for my initial time is probably pi. All right? Mm-hmm. And then the terminal point is where x equals 0. So the naive choice for my t is t equals 0, but this doesn't make sense. Right? Mm-hmm. So that's the tricky part. I have to make these 2 points as the initial time and the terminal pi such that its orientation is preserved. But because I choose my t to be exactly equal to x, so this is our choice of And by letting t goes from pi to 0, then I see this range of the parameter is not going to make any sense. Okay? Then what do we do? How can I make t goes from 0 pi, but x goes from pi to 0? How do you do that? So I fix my orientation first, but I want to have t goes from 0 to pi, and simultaneously x goes from pi to 0. How would you do that?
Did you do the inverse sign, so you have the inverse sign of 1 equals x?
I want to have the inverse sign, then it's going to be from 0 to minus pi,
Oh.
right? But you're really close. Taking the inverse and then add by pi. In other words, I make it pi minus t, this will do. If I make pi minus t, then t is equal to 0 initial time where x is exactly equal to pi. All right? When t is equal to pi, my x is exactly equal to 0. Not only that, I know sine of pi minus t is exactly equal to sine t. All right? Sine pi minus t is exactly equal to t. So this sine t is still equal to sine of x, all right? Because x is equal to pi of t. So here, this guy is equal to x. So this is also equal to sine x. So not only I can preserve my orientation, but also I didn't change the curve at all. So essentially, by introducing that parametric equations and that range of t, I will be able to parameterize this part of the boundary where the initial time is 0, where x is equal to pi, y is equal to 0. And terminal point is 0, 0, where this is corresponding to t equals pi. Okay? You can easily check the two boundary points. When t is equal to 0, x is equal to pi, y is equal to 0. When t is equal to pi, x is equal to 0, y is also equal to 0, right? Sine pi is equal to 0. All right? This is the parametric equation of the sine curve. And sine curve, ideally, is pretty easy. But because we have to follow this particular orientation, that makes the problem more challenging. Okay? In a line integral on the boundary, you have to take the orientation into consideration. Otherwise,